Hello everyone, and welcome back to Virtual Thermodynamics. Today, we're going to keep looking at air standard Brayton cycles, but we're going to see how we can increase thermal efficiency. For Brayton cycles, we know that when we're adding or removing heat, we tend to assume that the pressure is constant, and at least when we have ideal turbines and pumps, we assume that those processes are isentropic, or that they have constant specific entropy. We can do first law analyses on all our components, like we did in the Rankine cycle, and we can get equations for turbines and heat exchangers and compressors. Then we have to ask ourselves, what's the fluid? And in Brayton cycles, we assume that the fluid is air. When we have ideal gases, we can use the ideal gas law to move between states. But then we also have to think about whether or not we have constant specific heat or a cold air standard analysis, or do we have variable specific heat? And in either case, what we want to do is look for isentropic processes. Those always hold the key to these cycles that use air as a working fluid. We're going to use one of these two expressions, either the pressure ratios, if we're doing variable specific heat, or we want an equation with K in the exponent that in this case looks at the pressure ratios as well to find T. When we do that, we can get equations for either net work or efficiency. And in the problem we did in the last class, we saw that we had a thermal efficiency of 44.8%. Now that's reasonably high, but that was with a 4-component Brayton cycle. Maybe we can do better. So I sort of teased the fact that we have ways that we can improve efficiency. Remember, we like to improve efficiency because it saves us money and it reduces emissions. Just like a Rankine cycle, we can do regeneration, or preheating fluid before it gets into our heat addition stage. Like in a Rankine cycle, we can use reheat, so we can separate our turbine phases into a high pressure turbine and a low pressure turbine, and we can add heat in between. Something that's new in Brayton cycles is that we can do intercooling as well. We didn't do this in Rankine cycles because it doesn't take very much power to increase the pressure of a liquid like we have in a Rankine cycle. But in Brayton cycles, intercooling becomes important because it does take a reasonable amount of work to compress a gas. So here is what a Brayton cycle problem might look like when it has regeneration, reheat, and intercooling. Here, we can see that in the regenerator, we're taking the hot exhaust gas and passing it over our working fluid before it moves into the combustor. When we do reheat, again, we have a high pressure and a low pressure turbine, and in between them, we add more heat in a combustor. Intercooling works in a similar way, where in between our two compressors, we cool the fluid. Remember, when gases are heated, the gas molecules vibrate more, right? So there's more Brownian motion, and when we cool them down, that slows down. So it's a little bit easier to compress those air molecules. So we use all of these strategies in a Brayton cycle to try to improve the thermal efficiency. So why do we do regeneration? So before regeneration, we would add heat all the way from state 2 to state 3. But then at state 4 over here, we're exhausting to the environment some temperature that's fairly high. But when we do regeneration, what we do, we take that exhaust gas from 4 in this case, right? And we move to this intermediate state Y. And when we do that, the heat that gets lost from this fluid is transferred to the working fluid before the combustor. So we move from 2 to X. So with regeneration, we only have to put in enough heat. We only have to burn enough fuel, natural gas, to move from state X to state 3. So we save ourselves a little bit of heat by using heat that we've kind of already paid for, that we would otherwise just exhaust to the environment. Now, A lot of times when we're characterizing this regenerator, we want to look at something called regenerator efficiency. So we know that we're taking this hot exhaust gas and we're using it to preheat our working fluid before it goes into the combustor. That's what we do with regeneration. But the question is, how can we define an efficiency? So we have the actual amount of heat regeneration, and we want to divide that by the maximum amount of heat that we could transfer in our regenerator. So if we think of this temperature that we're exhausting at state 4, that's kind of like the temperature in an oven. So if you put, say, a frozen pizza or something into an oven, it can only heat up to the temperature of the oven. It can't heat up any further than that. So the maximum amount of regeneration we could have would be if the temperature at state X was equal to the temperature at state 4. So in real life, we always have a lower temperature at X than we do at 4. So we also have a lower specific enthalpy. So our regenerator efficiency is going to be the actual amount of heat that we transfer in the regenerator divided by the maximum amount of heat that we transfer in the regenerator. Or I can express this as H sub X minus H sub 2 divided by H4 minus H2. Regenerator efficiencies are typically on the order of 60 to 80%. So this is what regeneration would look like without reheat. So we can move from 2 to our X would be here, or maximum X would be when the temperature at X is equal to the temperature here at 4 prime. We'd have to heat then the fluid from this new state all the way up to state 3. Now the cool thing about reheat is that our exhaust temperature is higher than it was before. So now, at least theoretically, if we had 100% regeneration effectiveness or efficiency, we could increase our temperature at X all the way up to this new temperature 4. We'd have to put less heat in to get all the way up to state 3. So the interesting thing about combining regenerators with reheat is that there's some synergy in this case, or that they work better together than either one of them would apart. So another thing that we can do, which we're not familiar with from Rankine cycles, is we can introduce intercooling into our system. So here we go from having one compressor to having two compressors, and in between this first stage compressor and the second stage compressor, we cool the working fluid or the air. And that means we have to put in a little bit less work in our compressors to bring them up to the correct pressure. So here, for gas turbines with intercooling, we would have a state table without intercooling that would look like this, or not a state table, but a TS diagram that would look like this. But if we add an intercooler, what happens is in our state table, we add this little addition to our TS diagram, or this little bleb that sticks out over here. Now we remember that our net work and our net heat is equal to the area inside our cycle. So here we're adding more net work. In our process here, as we move from C to D, we're doing intercooling. Right? So here we've increased our net work and we've reduced the amount of work from the compressor. So that's why the net work increases, because we're putting less work in order to heat up the fluid. But the cost of that is that we have to remove some more heat. Okay, so now that I've sort of explained how to use regeneration, reheat, and intercooling, we're going to go through a problem that does all three of these things. Now this problem is a little bit long, so I'm not going to get numerical answers here, but I will walk you through the process, and I'll show you how to fix each state with variable specific heats and with constant specific heats. So a question like this is a little bit daunting because there are so many states. There are 10 states, but then each turbine and compressor has real and ideal outlets. So we get a lot of states on our state table. And when we first look at this, it looks like there's no way we could possibly have enough information to solve this problem. But in fact, we do, because we know the compressor pressure ratios. So the first thing that the problem asked us to do was start to draw a TS diagram. So I find the lowest temperature in the system, and I find the lowest pressure. And where those two things meet is my state 1. The problem tells me that state 3 happens at that same temperature, but I know it's at a higher pressure, so as my pressure moves up, I move from this 100 kilopascals up to some intermediate pressure that I'm going to use at states 3, 2, 7, and 8. And then I can connect state 1 to state 3 by first moving through an ideal compressor and then down to state 3. Now I know that I have my high pressure in my system, which is 1,000 kilopascals. And I know the maximum temperature in my system happens at state 6. So I can connect state 3 to state 6 by going through an ideal compressor and then all the way up on that constant pressure line to 6. You'll notice we don't have state 5 yet because I don't know where to put that point because I'm not sure where my regenerator is going to be yet. So now I go through an ideal turbine from state 6 to state 7 to this intermediate pressure. And then I'm doing reheat, so I heat my fluid back up to the same temperature it was at 6. And then I go through my second ideal turbine. And then my fluid cools all the way down to state 1. Now in this case, I do also have a regenerator. So my regenerator, the maximum temperature I could get at state 5 here would be the temperature at 7S and 9S. But in reality, it's going to be somewhere less than that. So I'll just put it here on my TS diagram where I'm showing state 5, but I don't know exactly where it's going to be. But I do also know that in order to preheat my fluid from state 4S all the way up to state 5, I also have to cool this exhaust gas from 9 down to 10. So I'll put state 10 on my TS diagram as well. Now this is what the TS diagram would look like if we only had ideal compressors and ideal turbines, but instead all of these devices are real. So for the real states at the outlet of these devices, I know that my specific entropy has to increase, but I'm going to stay on the same pressure lines. So I can draw state 2 to the right of state 2S and state 4 to the right of state 4S. Similarly, at the exit of the turbines, I can draw state 7 to the right of state 7S, but on that same pressure line, and state 9 on the right of state 9S. So now I've drawn my complete TS diagram, and I don't think there will be a problem that you see in introductory thermodynamics for mechanical engineers that has a TS diagram with more states on it than the one that you see here. But it doesn't really matter how many states there are because we have a systematic process to go through and solve this problem. You probably wouldn't see a state table as blank as the one that I've shown here for a problem like this on an exam, but we can ask you how to do any single part of this problem on any exam that we ask you. So it's good to see the whole process. So now we're going to do the first law on all the components in this system. So the thermal efficiency, right, or at least we could, right? And if we did, we know that we'd get, typical answers for our turbines and our compressors, which work like pumps, where we'd get m dot times h in minus h out, and we'd let the first law tell us what the signs are. And if we're in a heat exchanger, right, like our combustors, we're going to get m dot times h out minus h in. But then we're going to see that we also have to do kind of a special case of the first law on the regenerator when we get further in the problem. So to characterize this particular cycle, we want the thermal efficiency, which is the net work over the heat in. Right? If we divide everything by the mass flow rate, we can get equations for the power generated by the turbines and the heat that we're putting in the combustors. Right? So this is a function of just the specific enthalpies because we're doing this as power per unit mass flowing through the system, or the same with heat. And then if I'm going to do a cold air standard analysis, I can factor out the specific heat from the top and the bottom, and the specific heats will cancel. So if I'm doing a variable specific heat problem, I need to find all the H's. And if I'm doing a cold air standard problem, I need to find all the temperatures. I might also be interested in a backwork ratio, which is going to be the power consumed by all the pumps, or in this case we call them compressors because the working fluid is air. And I'm going to divide that by the power developed by all the turbines, remembering that my power plant's first customer is my power plant. So for here, my backwork ratio, I like to take absolute values here because the signs of the pump power and the turbine power are different. So I got to remember to take absolute values here. And again, I can get this all as a function of the specific enthalpies through these components, or I can factor out Cp if I'm doing constant specific heats and get this all as a function of the temperatures. So these are symbolic solutions for everything that we need to know for this problem. But what we need to do now is fix the states, either to find H in a variable specific heat problem or to find T in a constant specific heat problem. So now, how do we fix the states? I can see I drew a pretty big state table here, but I don't need to know all the isentropic states for my answers. None of those equations talk about 2s or 4s or 7s or 9s, but I need to know them in order to find the real exits to all my compressors or my turbines. So if we're going to use the air standard analysis, then we want to look things up on table A22. If I'm going to do a cold air standard analysis, then all I need are the temperatures and the pressures, so I don't need to look up things like H or S or specific volume. So if I was doing this numerically, I would look all of these up on my states. The other thing that I want to do, which I've sort of already done on my state table here, is I want to identify where the isentropic processes are, because the isentropic processes are always the key to finding the answer for these cycles that use air as the working fluid. So as I move from state 1 to state 2, I'm going through, or to state 2s, I'm going through an isentropic compression. So if this was an air standard analysis, I would need to actually find delta H. So I would use my pressure ratio. So I was told the low pressure and the intermediate pressure. So then I know this pressure ratio, and then I can find, because I've already fixed state 1, I can find PR1, and then I can find PR2 and use that to fix the rest of the state. So that's what I would do in the air standard process using table A22 in the textbook. If this was a cold air standard problem, I wouldn't need to find the enthalpies. Instead, I just want the temperatures. So I can remember that delta H is equal to Cp times delta T. I need to know T2, and this is, or T2s, right? So this is the temperature at the end of an isentropic compression. So I remember that this is a problem where the working fluid is air, and I know the pressure ratio, and I'm looking for an equation with K in the exponent. And if I have that, then I can only apply it when the process is isentropic. But this is an isentropic compression, so I can use this to find Ts. Now, if I fixed Ts, then I want to move from Ts to state, or from state 2s to state 2. So now I need to know the isentropic efficiency for the compressor. So I remember that for, this is, I've written it for the turbine, but for the compressor, the ideal turbine consumes less power than the real turbine. So the equation is right, even if the efficiency has the wrong subscript. And I can find this for my H's, right? So I can get this as an expression of my specific enthalpies. Or if I'm using cold air standard analysis, then I can factor out the CPs and get this as a function of my temperatures. And at this point, because I've already fixed the isentropic outlet of the first compressor, the only thing I don't know in this problem is either H2, if I'm doing variable specific heat, or T2, if I'm doing constant specific heat. So now state 3 is fixed because I know the temperature. So if I know the temperature and I'm told the pressure, because state 3 happens at the same pressure as state 2, and if I know that, I can look up things like enthalpy on my table A22, or I just already know the temperature and the pressure because if I'm doing a cold air standard analysis. So next I would move to state 4s, and here the process is the same as when I went through my first isentropic compressor. So this is basically the same. So I'm trying to find delta H if I'm doing a variable specific heat problem, and I can isolate and solve for PR4. I know everything else in this equation. I get things from A22. So I would have had to take the temperature that I know at state 3 and find PR3 as well. Or if I'm doing cold air standard, I know that this is Cp times delta T, and I use this same expression with K in the exponent that's a function of my pressure ratios. I can only do this for the isentropic part, and then I can find the temperature at state 4s. As I move between 4s and 4, I'm going to do the same thing that I did through my last compressor, where we have this equation for the, it should again say compressor efficiency, and then I can get this for variable specific heat or for constant specific heat. And again, the things that I don't know are H4 or T4, and I can solve for those directly from this equation. So now, as I go from state 4 to state 5, I'm going through my compressor. So I would want to know my compressor efficiency here. And if I did know compressor efficiency, then I can just work this out. Because if I know my regenerator efficiency, then the only things that I don't know here, although I guess I don't know T8 yet, right? So here I can at least get an expression for my regenerator efficiency as either a function of enthalpies or of temperatures. Note that in the previous section, when we were looking at regenerator efficiency, we did know state 8 because the temperature here is given. And when the temperature is given, that's all we need for cold air standard analysis. And it's all we need to fix our state on table A22 if we're doing variable specific heat analysis. And then as I get to state 6, I'm told the temperature and I know the pressure because now this is at the high pressure in my system. I can go between that first isentropic turbine from 6 to 7s. This looks the same as the compressors, but my compressor ratios will be flipped, or my pressure ratios will be flipped because now the pressure is going down. I can find PR4 in a variable specific heat problem, or I can find PR6 in a variable specific heat problem, or I can find T6 in a constant specific heat problem. As I go from 7s to 7, what I need to do is look at turbine efficiency, now with the correct substrate or subscript, and I can either get that as a function of the enthalpies, where I know the specific enthalpies except for H7, or as a function of temperatures in a cold air standard analysis, where the only thing that I don't know is T7. As I move between state 8 to state 9, so state 8 is known because I know the temperature, and it's at that intermediate pressure. And then as I go from state 8 to state 9, I'm moving through this isentropic turbine again. So I'm trying to find delta H, and I can use that by the pressure ratios between 8 and 9s. Remember that we're setting up these ideal outlets from our turbines and our compressors to have the same pressure as the real outlets. Again, I can find PR8 because I know everything else in this problem. Or here I know PR8, so actually I'm solving for PR9. And then I can get delta H. So again, I know T8, so I would be solving for T9s here. And then I would find 9s from this equation with K in the exponent. As I move from 9s to 9, I'm going to use my turbine efficiency if it's given. And again, the only things that I don't know here are the real outlet specific enthalpy, if I'm looking at variable specific heat, or the real outlet temperature, if I'm looking at constant specific heat. So now again, as I'm moving from 9 to 10, I've got more going on in the regenerator. So now what I want to do is I want to do the first law analysis on the regenerator. So in the regenerator, I know that it's at steady state, that there's no change in kinetic energy, no change in potential energy, or at least the changes here are small compared to the changes in the enthalpies. It's adiabatic and passive, so it's not consuming or generating power, and it's fully insulated, or it's not losing heat to the surroundings, even though there's heat being transferred from the hot side of my regenerator to the cold side of my regenerator. I'm assuming that there's no friction loss and no heat loss anywhere in my regenerator. So if I do this, I can get an equation for H10. And if I know H10, then I can solve the problem. I know now the exit of my regenerator, so the exit into the atmosphere. And if I'm doing this in a cold air standard analysis, then I also know that I can find my temperature at state 10, which is the temperature of the exhaust gas. So I know this was a long one, but thanks for sticking with me for this Brayton cycle with all the trimmings. And I'll see you next time on Virtual Thermodynamics.